This video is an introduction to the derivative. So one thing that we may remember from previous classes is that the slope of a secant line of any particular function f of x is f of b minus f of a over b minus a. So this just represents the slope between these 2 points, and then I can draw a line that goes between those 2 points. So that's basically what's going on with a secant line. And if I look at this particular graph on Desmos, what I can see is if I write the equation of this tangent line, or the secant line, I'm sorry, we have y minus the y value equals this slope times x minus the particular x value. And if it changes, if any of the values change, then what I end up with is a different slope, which then I can connect these 2 points with. So now the question becomes, what happens as these points get really close together? So if you notice, these are secant lines, but then what happens if this gets really close together, really close together, really close together, really close together? If I end up at one point, I don't have a secant line anymore. And what you notice is that I would have a denominator that's equal to 0 and a numerator that's equal to 0, right? So what I have is I have this slope that's an indeterminate form. I have a slope that if I have f of 1.4 minus f of 1.4, that's 0, and 1.4 minus 1.4 is also 0. So I end up with this issue. I can't just use this equation to get a tangent line. I can only use it to get a secant line. So how do I deal with that if I want a tangent line? Well, since it ends up becoming an indeterminate form, what I want to do is I want to take the limit of the secant line slope as those 2 points get infinitely close together. And then what this is going to do is this is going to take the secant slope and turn it into a limit as the difference between these two things goes to 0. And so the limit as the difference between these 2 points goes to 0 is going to end up giving us, so let's say they would meet here if I move them both, I'm going to get a tangent line that goes right off of the graph instead of a secant line that goes through 2 points of the graph. So that's basically what's going on, is we're taking this line's slope, or the slope of the secant line, and taking the limit as these two things approach the same value. So that's kind of what we're doing. Find the average rate of change between 0 and 1 for this function. So that would be f of 1 minus f of 0 over 1 minus 0. And so f of 1 is going to be 2 minus 7 is negative 5, plus 5 is 0. And then if I plug in 0, I get 5. So the average rate of change is negative 5. That represents the slope of the secant line between 0, 5 and 1, 0 on this particular graph for f of x. So now what we're going to do is we're going to find the slope of the tangent to the curve at this point. So remember, the secant line between, or the secant line connecting 0 and 1, 0, 5 and 1, 0. So let's say that's 0, 5 and that's 1, 0. It's not quite the vertex, but there's my slope there. What I'm trying to do is I'm trying to take this parabola, and at x equals 1, I'm now trying to find the slope of this tangent line. So what I would do is I would say the limit as x approaches 1 of f of x minus f of 1 over x minus 1. So f of x, I have to continue to write limit until I actually substitute 1 in. So I have 2x squared minus 7x plus 5 minus f of 1. So what was f of 1? F of 1 was 0 over x minus 1. So now I continue to do the algebra. Limit as x approaches 1. If I'm going to factor the numerator, notice that I subtracted 0. That doesn't really do anything. So I factor it. I have 2x and x. I have minus 5 minus 1. So then I end up with, if I multiply it back out, 2x squared minus 7x plus 5. Notice that the x minus 1s will then cancel. So now I have the limit as x approaches 1 of 2x minus 5. And now I can just directly substitute 1 in after I did some algebra stuff, and I end up with negative 3. So this is the slope of the tangent line to the curve. Now if I want to write the equation, I just remember that 1 comma 0 was the point. So I write y minus 0 equals negative 3 times x minus 1. Find the average rate of change for between 2 and 3 for this function. So that's f of 3 minus f of 2 over 3 minus 2. So if I substitute 3 in, I get 4. If I substitute 2 in, I get 1. So I end up with 3. So the average rate of change is 3. So that's the slope of the secant line. Now if I want to find the slope of the tangent line, I have to take the limit as x approaches 3, because we're trying to find it at 3, of f of x minus f of 3 over x minus 3. Now remember that f of 3 was 4 in this problem. I already found that. So f of x is 3x minus 5, and then f of 3 is 4 over x minus 3. So now I do some algebra, and this is actually a good point that we have to make sure that we're careful of. Continue to write limit until you actually make the substitution. So that was my fault. So limit as x approaches 3, 3x minus 9 over x minus 3. I can factor out a 3 from the numerator. And again, don't forget to write your limit as x approaches 3. Now the x minus 3's cancel, and so I'm just left with 3. So the limit as x approaches 3 of 3, I don't have any x's to plug in. So this is the slope of the tangent to the curve of that. And then if I wanted to write the equation of the tangent line, that was not the question, but I could say y minus 4 equals 3 times x minus 3, because the point was 3, 4. Again, this is not the question, so you don't have to write it in this particular case, but if that was the question, that's what we would write. Find the average rate of change between 1 and 2 for this function. So f of 2 minus f of 1 over 2 minus 1. So this is the slope of the secant line. If I substitute in 2, I get 8 minus 8 plus 2 minus 1. So f of 2 is 1. And then if I substitute in 1, I get 1 minus 2 plus 1 minus 1. So that would be negative 1 over 2 minus 1. So that's 2. So the average rate of change is 2. That would be the slope of the secant line. And if I wanted to write the equation of a secant line, I could say y minus 1 equals 2 times x minus 2, because I know the point 2, 1 is on the secant line. I also could say y minus negative 1 or y plus 1 equals 2 times x minus 1, because I know that this point, negative 1, 1, 1, negative 1, is also on the secant line. Again, this is not the question, but if it was, I could say that. Find the instantaneous rate of change. So this is not asking for a tangent line. This is just asking for the slope of the tangent line at x equals 1. So limit as x approaches 1, f of x minus f of 1 over x minus 1. So the limit as x approaches 1 of x cubed minus 2x squared plus x minus 1. And then remember that f of 1 was -1, so minus -1 over x minus 1. So now I'm just going to continue to do algebra. Limit as x approaches 1. -1 minus -1, those end up canceling off. So x cubed minus 2x squared plus x over x minus 1. Now it's factoring time. Limit as x approaches 1 of x times x squared minus 2x plus 1 over x minus 1. Continue to factor. Limit as x approaches 1 of x times x minus 1 times x minus 1 over x minus 1. One of these x minus 1s cancels. So now I have the limit as x approaches 1 of x times x minus 1. And if I plug in 1, I get 1 times 0, which is 0. So the instantaneous rate of change, or the slope of the tangent line at the point 1, -1, would be 0. So what that means for our graph is it would look something like this. At the point 1, -1, our slope, and I don't remember which one it is. Actually, it would be this one. Our slope of the tangent line would be 0. So that means that it actually is like one of the curve hump things. So it's like either the top or the bottom. It's where there's what we will in calculus call a local maximum or a local minimum. So in this case, it's a local minimum. The volume of a right circular cylinder of height 9 feet and radius r feet is volume equals 9 pi r squared. Find the instantaneous rate of change of the volume with respect to the radius at r equals 3. So what I will do is I have this v of r. So I need to take the limit as r approaches 3 of v of r minus v of 3 over r minus 3. So I'm just doing the exact same formula here. So I have the limit as r approaches 3 of 9 pi r squared minus what happens when I plug in 3. I get 9 times 9, which is 81 pi over r minus 3. Limit as r approaches 3 of 9 pi is factorable out of this. So I have r squared minus 9 over r minus 3. And as you can see, what we're noticing every single time we do this is that something ends up canceling out with the denominator. If it doesn't, we probably did it wrong in one of these problems. So now I have the limit as r. I lost which variable I was doing. R approaches 3 of 9 pi times r plus 3. So I just plug in 3 and I get 9 times 6, 54 pi. So that's the instantaneous rate of change of the volume with respect to the radius. So in calculus, we would say that's dV dr, but you don't need to know that yet. So dV dr would be 54 pi.